Okay, now let's continue to discuss the system we have for the closed loop control. So for this example, right, we remember we have this transfer function here, the closed loop transfer function. Let's say we say close. Let me get the pen working here. Okay, let me use my. Okay, so the closed loop transfer function is closed loop transfer function is GS equals K C1 divided by S plus C2S plus K C1. Okay, so now let's do further analysis on this particular scenario after we put this control system with scaling constant K. So one way to look at this, how the system behaves, is actually the body plot, right? So we want to see the performance of the system, let's say, from body plot, okay? So with different number of Ks, the body plot. Okay, so I have this kind of MATLAB running here. So I wrote the just give before we put this MATLAB simulation, I would like to bring actually one example we used here. So remember in one of the lectures, let's see, lecture 24, we have example of a DC motor here, and the spec is here. We have KT, KB, we have R, we have beta. We ignore this inductance here, L. Now we also have the inertia, right? So in this case, we have example DC motor. What we have is KT equal KB equal 0.031. Now we have R equal 0.82. Now we have beta equal 1.81 times 10 to the minus 6. Okay, then we have m. In this example, we say we choose m is the inertia, which is 5.65 times 10 to the minus 6. Okay, so this is the example DC motor we have. So then from this we can compute this C1 and C2, right? So remember the C1. Let's see, the C1 here equal our M R K T, right? So if we plug in all those kind of numbers, what you get is 6,691 approximately. Okay, so you will get a C2 will be approximately 207. Okay, so then we plug in all those kind of numbers and to do some simulation. So the from MATLAB you can write very simple the body plot and put all those kind of numbers in as what I put it here. As you can see, it's very simple example, and you can compute C1, C2, and then you do the body plot. And for this situation, we tried three kind of cases: k equal 1, the controller k equal 1, k equal 10, and k equal 100. So what we are trying to see here is if you run this code, you'll see three different kind of body plot, right? So here we have three different kind of body plot, and this blue one is actually the one with k equal 1, and this kind of orange one, which is k equal this orange one is, or yellow one, this one is about k equal 100. As you can see from the body plot, remember this the body plot things, and here it's this resonant frequency, and from this face, has some overshoot, and from the face information, you can see how the system actually responds. Remember, if this is the narrower of this jump in the face domain, the quicker the system will respond, right? So this is to give you some some idea. If we change k, actually we change the behavior of this second order system, which makes sense, right? So we starting with something like there are no overshoot, more or less like a first order system. Then we get into something like second order system behavior, which has overshoot. Okay, so now there another way to look at this this system is we try to do more analysis. Okay, what we are trying to see is we have roots, right, for the second order system, and for the pose we try to find out if we have different k, what kind of pose it will look like. Okay, let's say the pose of this system, the pose, and this will be roots of the characteristic equation. Characteristic polynomials, or here we say polynomials. So which is for this case is s plus c2 s plus k c1, right? So we try to find the roots of this. Now of course this will be 2 minus c2 plus minus c2 squared minus 4kc1. From the last lecture, we know if as long as k is positive, the system will be stable, right? So we already established that concept. Now let's see what we can do to do further analysis. So obviously, if if c1, c2, let's see what's going on. So let's see here. It's let's delete this. Can I delete that? That's interesting. I cannot delete this. So let's say here we have I probably can erase with this. Okay, good. So I can get rid of this now. So with this Adobe. So here we say we have these roots, and if c2 squared minus 4k c1 larger than 0, or this means if k less than c2 squared divided by 4c1. Now if this under this scenario, and this both roots are both roots will have roots all real numbers, right? Basically, the real numbers meaning the system behave more or less like a two first order system. If we plug in all the numbers, we will have if k less than the number, what I find out is about 1.61. So this will be the first order system. This behave like a two first order system. Okay. Then if obviously if k larger than this 1.61, then they will have the roots will be complex number. Okay. Okay, roots will be complex number, and the imaginary part imaginary part will be square root of 4kc1 minus c2 squared, and the real part, of course, here we need to divide by 2. The real part will be c2 divided by 2, right? It's a minus. Okay, so from here you will see the real part is always constant. ，Hello，你用关了？哦，那我那反正我给你们送过去呗。